All right, let's dive in deeper to chronoamperometry by examining the concentration profiles that develop after we take that potential step. In the previous video, we covered the governing equations and initial and boundary conditions that led to the Cottrell equation. As part of that solution, you get these concentration profiles that come out. Here we have the concentration profile for our reactant, which is our oxidized species in this case. And here we have the concentration profile for our product, which is the reduced species in this case. This is under the case where we're taking a strong reducing step potential so that we're in the diffusion limited regime. And we're also assuming that we have a soluble product. In this plot here on the right, you're going to see lines plotted that are solid. Those are for our reactants, and you'll see lines plotted that are for the product, which are dashed lines. On the y-axis, you have the ratio of our concentration relative to the initial concentration, which if you recall, that's just the bulk concentration of our species. And then along the x-axis, we have the distance from the electrode. Initially, all we have is completely flat concentration profiles. No product, indicated by this dashed line at 0, and our reactant is at the bulk concentration, indicated by this flat line at 1. We've let a little bit of time pass, 1 millisecond, and we've depleted pretty much all of the reactant next to the electrode, and we've started to build up product next to the electrode. We have this sharp concentration gradient and this narrow diffusion layer. After 10 milliseconds, that diffusion layer has grown a bit thicker. We're reaching further into solution to get reactants to react at the electrode, and products are diffusing further into the solution as indicated by this dashed line extending further out. We can watch this trend evolve with each time step. Here we're seeing the diffusion layer extend further out at 100 milliseconds, even further at 400 milliseconds, and further still at 1 second. As you can see here, the diffusion layer is growing thicker and thicker with time, and my concentration profiles are getting shallower and shallower with time. What that means is that my current should be reducing with time because my current is proportional to my concentration gradient according to Fick's first law. So that makes sense that when we see our current response, I versus T, that we see this initial spike and then this decay. And this is where that decay with 1 over T to the 1/2 comes from, because this diffusion layer thickness is growing with time. Now, what's different if I have an insoluble product? First of all, I don't have any outward diffusion of my product. My reduced concentration in solution stays at 0. So does no outward diffusion impact the Cottrell equation? Mathematically, theoretically, no, it doesn't, because we don't even consider the product in deriving the Cottrell equation. Practically, it can. And we're going to discuss some of those ways in the next video. But for now, we're just going to focus on the pre-concentration of the product at the electrode. And what I mean by that is that when you have an electrode, indicated here by this striped line, when the product is insoluble, it builds up on the surface here. And so you have a bunch of product just pre-concentrated right at that surface of your electrode. And it's all ready, waiting to oxidize or reduce when the potential becomes more positive or negative than the equilibrium potential. And when that happens, the diffusion layer next to the electrode just becomes flooded with the reactant. So if it was a reduced species, all of a sudden I'm dumping a bunch of my oxidized species right into the solution right next to the electrode. How does this impact a CA measurement? Well, your first potential step that you do, it won't impact. But the following potential steps that you do, it could impact it if you don't wait long enough to reset the diffusion layer. What do I mean by that? Let's take a look at it qualitatively. So resetting the diffusion layer after CA means that we're trying to get back to the initial condition of the bulk concentration everywhere. So here on the left, we have a soluble product, and you can see in the plot below that we have the soluble product profile plotted in the light red line. So if I do a 1 second chronoamperometry step, and then I reverse it. So if I was doing a reduction step, I would then step more positive to then reoxidize my reduced species back to the oxidized species. And if I take a snapshot just very briefly after reversing it, 0.1 seconds after it, what would my concentration profile of that reduced species look like? If you want to think through it, go ahead and pause the video and think through it. Here's what it would look like. Immediately when I do that reverse step to start oxidizing my reduced species back, and if I do it large enough that it's in the diffusion limited regime, my surface concentration will drop to 0 for the reduced species. And then it's going to take some time for the reduced species out in solution to diffuse towards the surface of the electrode. So I'll have this rise and then this fall. And so I need to wait long enough for the reduced species out here to diffuse towards the electrode so that it can all be converted back to the oxidized species, and my concentration profile for my reduced species can return back to 0. Now, what about for an insoluble product? Remember, we don't have any of the reduced species in solution. So if we look at the plot here on the right, we're actually plotting the reactant, the oxidized species in this case. And what is that concentration profile going to look like after 0.1 seconds? So if we did a 1 second chronoamperometry, where we're reducing the oxidized species and then we reverse it so that we oxidize the reduced species back, what's that going to look like? If you want to think through it, go ahead and pause the video. What's going to happen is I have all of that reduced species sitting right against the electrode, and immediately it's going to oxidize when I go to a potential step in the positive direction. So I'm going to be dumping a bunch of oxidized species next to the electrode, and then eventually, when I get far enough away, I'll go back to the bulk concentration. So I need to allow enough time after reversing my potential step for this oxidized species to all diffuse back out into solution and reset this flat concentration profile at the bulk concentration next to the electrode. That does it for explaining the concentration changes next to the electrode during chronoamperometry. I hope you'll join me for the next video, where we dive into all the ways that chronoamperometry can go off the tracks and the non-idealities that can show up during those measurements.